I'm from Panasonic R&D Center, Singapore. I would like to present our work on mobile robot and cloud-based integrated defect inspection system for indoor environments. First, I'll give a brief idea of the needs for defect inspection system and the problems with existing approaches. And then I will provide a brief overview of our system design, the operations and methods. And then I'll go into some specific details of our novel contributions. And I will conclude with some video and results from our site trial. Panasonic R&D Center provides technologies for other Panasonic divisions, and also we work with regional partners in Singapore. So we also work with Building and Construction Authority, which is a statutory board under the Singapore government, which ensures the quality of the built environment sector in Singapore. They use the CONQUAS standards, that is the Construction Quality Assessment System standards, for evaluating the quality of the buildings. And they also use CONQUAS banding for rating the workmanship quality of developers in Singapore. So that directly affects the selling prices of the residential units they are constructing. So there is real monetary value in delivering high quality homes to customers. CONQUAS mainly focuses on three main areas: internal finishes, external finishes, and the functionalities. We focus mainly on the internal finishes, specifically on alignment and unevenness, cracks and damages, stains and patches, etc. Because this contributes to the major score in the CONQUAS total score. The existing approaches are quite manual, like predominantly manual, and they suffer from problems such as inaccuracies, lack of manpower, and difficulty in upskilling. And the automated inspections are still under research stages. And some of the problems are like it is very difficult to transport to the site, and it takes a really long setup time to do the inspections for the robot. And defect inspection in general, it requires handling large data and high computation, which is not very suitable for edge computing. And there is no centralized defect management system for sharing of information between different stakeholders. So there's no traceability, and it always leads to miscommunication and rework. So our objective was to build an automated defect inspection system to achieve fast and accurate construction quality inspection, and with intuitive user interface for robot control and defect visualization. So our system consists of three main components. The first is an autonomous mobile robot, which is a wheel platform able to autonomously navigate within residential units, and it just uses the floor plan for localization. So there is no mapping involved, so there is no additional setup time that is necessary. And we have made it in such a way that it is lightweight, easy to carry to the site, and with long battery life. It uses Leica BLK 360 sensor, which collects point cloud and camera image data. So this data is then transmitted to our second component, which is a high computation power remote server, which does our 3D and AI analytics to identify the defects in the data. And these defects can then be visualized on our third component, which is a UI, intuitive user interface, where we can see the defects visualized, and also we use it for robot control. So before inspection, we need to prepare a floor plan data that is from the 2D drawings or from the BIM. So this work is done manually. So this serves as a method for our localization of the robot. Traditionally, during inspection, 2 inspectors are required for doing the defect inspections. So our proposed method, we only have 1 inspector and 1 robot. So the inspector takes the robot to the site. He uses the user interface to create an inspection, and he selects one of the 3 different modes of operation of the robot. So the first mode is just a manual mode where he can teach the robot a particular scan route, and mode 2 is a mode where we can choose a pre-planned scan route, and the robot will autonomously travel to these locations, collect the data. The third mode is the ability of the robot to automatically find its own optimal scan path to collect the data. So while the robot is doing the inspection, the inspector can continue to do other inspection modules such as functionality checks, etc. So from our experiments, we observed that the effective range of our Leica scanner is only 3 meters, because CONQUAS requires an accuracy of 3 mm. So we need to scan more data, more points from the floor plan. So we utilize the sensor range, visibility, and incidence angle. So these are the three key parameters which we observe that affects the defect detection capability. And we use a spatial optimization technique called as a weighted centroidal Voronoi tessellation, where the Voronoi centers are giving us the optimal scan poses, and we then use a shortest path planner to identify the scan route. And then the data that is collected from the scanning for the inspection is then compressed using MPEG and JPEG compression techniques to achieve manageable sizes. So it is easy for us to transmit the data to the remote server. So once it's there on the remote server, we do some pre-processing. All this is done automatically. Like for example, we extract the planes and remove the other objects like dynamic objects, which is not necessary for defect inspection purposes. And then we do 3D and visual fused semantic segmentation. So here we use the information coming from both the structural and the visual part from the point cloud and the images to achieve a very fine semantic segmentation. So this we use it for filtering the defects in our later analysis stages. So the 3D geometric analysis and AI-based image analysis helps to identify the defects. They are all automatic. And here we have some examples of some of the unevenness of warpages that we can see on the actual real construction site. And we also see visual defects such as cracks and stains on the wall. And finally, all these defects can then be projected onto the floor plan. So it can be visualized on the user interface. So this is a video of the demonstration. So here we have, we select the robot, we give it a floor plan, select an approximate initial position, and then we allow the robot to traverse autonomously within the flow, and it can collect the scan data. So once it is, once the scan data is collected, transmitted to the server, we are able to see the defects on panoramic view, on the floor plan, and also a photospherical view, and we are able to like categorize the defects based on the components and also based on the room segmentations. And in the end, we also deliver in the report in the form of the required form as per the CONQUAS standards. So finally, this is a comparison of the timings that we did based on mobile robot and manual. So total inspection time for mobile robot is about 45 minutes, while for manual it is about 35 minutes. It might seem slightly slower, but we have a significant saving when it comes to report generation, because we are able to generate the report in seconds compared to a human who takes several hours, and we get highly precise localized defects and in the floor plan. And some of the problems that we faced are lack of ambient light, lack of network signals, and like false detections. We had to do some workaround for all of this. And to conclude, I've presented an integrated system with 3D and AI on the cloud with an intuitive user interface. So we have tested in real construction sites, and we look forward to improve and commercialize our system. So keen to understand the scenario in India as well. Thank you.